In this video, we're going to continue with differentiation, and we're going to look at the first of two videos on optimisation. Now, optimisation may or may not be a new word to you, and basically optimisation means that you're trying to find the best solution from all feasible solutions. And there are many real life situations which involve finding the greatest or least value of a function subject to some kind of constraint. And this constraint will be true no matter what our solution is. So for example, the side length of a box. Now you'll see what I'm talking about when we go into the example for this one. So the type of optimisation problems which might be of use at some stage are maximising an area to be fenced in. So for example, if you're landscaping your garden, or maybe you're looking to fence in an area in a field or something like that, or you might be minimising the cost of producing a container, for example. So for instance, if you think about packaging in a supermarket, so if you were in a supermarket, basically think of all the different packaging that you get for different items that you can buy, and what those companies have possibly done to try and minimise the cost of producing the boxes and the containers for those items. So without differentiation, we would need to plot most functions to find their maximum and minimum values. And we've already seen that from the last video as well on maximum and minimum values. But with differentiation, we are able to find stationary points, and therefore we can easily identify the maximum and minimum values. So let's look at an example here. Now, there isn't particularly much new information here, but I suppose the thing with optimisation is just trying to get your head around the situation in the question, and that is the bit that people need to think about the most. So it's not the actual maths that causes the issues here, it's the just trying to understand what's going on in the question. So this example then, a square piece of card of length 30 centimetres has a square side x centimetres cut from each corner, and we can see the diagram is here. An open box is formed by turning up the sides. So part A asks us to show that the volume V of the box can be expressed by 900x minus 120x squared plus 4x cubed, and part B asks us to find the maximum volume of the box. So the solution then. So firstly, obviously, we're going to look at part A, and we'll just pay attention to what the question is telling us. So it's a square piece of card of length 30 centimetres. So we can see that the length and the breadth here are both 30 centimetres, and it has a square of side x centimetres cut from each corner. So I'm going to label all of that there to keep myself right. So you'll see there that it tells us that the box is formed by turning up the sides. So if you think we've got this square here that I've put in, and I've got these rectangles at the side here. So these little squares, they're gone. So we've turned these rectangles up and we've got an open box. Now, if you think about the length of this base then, that is also a square, and it's going to be 30 minus 2x. Sorry, there's the open box there. And you can see that we've got 30 minus 2x here along our base. So those two lengths are the same, still a square, and the height then is x centimetres. Okay, because the squares that were cut from each corner were x centimetres, and that's also the length of the rectangles which were turned up to form this open box. So we've got the box here, we've got the length, we've got the breadth, we've got the height, so we are able to find the volume. So the volume is equal to the length multiplied by the breadth multiplied by the height, and that is x multiplied by 30 minus 2x multiplied by 30 minus 2x. So I'll expand my brackets firstly, so that's x multiplied by 900 minus 120x plus 4x squared, and expanding that further, I get 900x minus 120x squared plus 4x cubed. And you'll see that's what I was asked for in the question, so I can write as required. So just now would be a good time to pause the video and take down the working for part A and then come back for part B. Okay, welcome back folks. So, part B of this question, we want to find the maximum volume of the box. Now, even if you hadn't been able to do part A, we can still do part B, because what we need in part B, we want to find the maximum volume. Well, we've already been given the volume in part A, the expression for the volume. So even if we didn't find that in part A, we already knew it. So we can just use this at the start of part B anyway. So the volume was 900x minus 120x squared plus 4x cubed. So we're going to differentiate this because we want to find the maximum volume. So remember, if we differentiate, we can find stationary points, and those are either maximum or minimums. So we've got dv by dx is going to be 900 minus 240x plus 12x squared. And we know that maximums occur when dv by dx is equal to 0. Now you could write stationary points here. Stationary points occur when dv by dx equals 0, but I know I'm looking for a maximum, so I can just write maximum here as well. So 900 minus 240x plus 12x squared is equal to 0. I can divide throughout by 12, and that leaves me with 75 minus 20x plus x squared equals 0. Now, I'm just going to rearrange that so that I've got my highest power of x at the start of my expression. And then I can factorise that. I get x minus 15, x minus 5 equals 0. And solving each of these, I get x equals 15 or x equals 5. Now remember, x was a length. X was what we were cutting from each corner here. So you can see we've got two options. So let's look at the first option for x equals 15. So this would be the square of length 30 that we talked about in the original question. And if we cut a square of side 15 centimetres from each corner, well, what's actually going to happen here? Well, we're actually going to be left with nothing. So that isn't a feasible solution. So when I first introduced optimisation at the start of this video, I'd said here there might be some sort of constraint on the problem. And I said, for example, the side length of a box. So here we know that our squares that we are cutting here, well, they actually have to be less than 15 centimetres, because the minute the squares we're cutting out are 15 centimetres, there's no box left. The square disappears completely. Now, if we look at this, if we cut squares of side length 5 centimetres from each corner, that's fine, that works, and we're still able to make this open box, so that still works for us. So we can say that x is equal to 5 centimetres, since x has to be less than 15 centimetres. So we need to state why we are choosing 5 here and not 15. So we now need to prove that this is a maximum. So we need our nature table. We know that x is equal to 5. We've got dv by dx, and we need our shape. So we know when x is equal to 5, that dv by dx is equal to 0, and therefore the gradient of the stationary point is 0 there. So we can just represent that using the small horizontal line. Now we can look at points on either side of the 5. Now, say this was in a non-calculator paper. I wouldn't particularly want to choose, for instance, 4 and 6, because it's probably a bit more arithmetic than I need to do here. So say I choose 1 and 10, it actually makes this slightly easier. So for 1, I would have 900 minus 240 plus 12, and that gives me a positive answer. So the shape of my graph is increasing. Now using 10, I would get 900 minus 2400 plus 1200. That gives me a negative, and my graph will be decreasing. So you can see here from my nature table that I've got a maximum when x is equal to 5 centimetres. Now, we're not actually finished yet, because the question actually asked me to find the maximum volume of the box. So the volume was 900x minus 120x squared plus 4x cubed. And I want to know what that is when x is equal to 5. So I can substitute that in, and that gets me 2000 cubic centimetres, which is my final answer. So just now, folks, would be a good idea to pause the video before the screen goes blank and copy this down in your notes.